In this video, we will investigate several more examples involving the comparison test, limit comparison test, ratio test. But more importantly, we will once again discuss a bit of the intuition, i.e. the thought process involved. So consider the following series. Now the observation I'm going to make that I've made previously is, to me, the most important thing to look at in this case would be kind of the biggest terms in the top and the biggest terms in the bottom. So the square root of n plus 1 divided by n squared plus 1 is going to behave like, so the squiggly here just means it's going to be like, the square root of n over n squared. Now at this point, the observation I want to make is that there's no direct comparison here in terms of an inequality. We've made the top smaller, which typically makes a smaller overall quantity, but at the same time we've made the bottom smaller, which typically makes a bigger overall quantity. So this doesn't look like something where I want to use a comparison test. So I'm just going to note here, no comparison test. There's no obvious inequality to add. But note, square root n over n squared algebraically is equivalent to 1 over n to the 3 halves. And the sum of 1 over n to the 3 halves is a convergent p-series. So since I would like to use a comparison test, I don't have that inequality, I'm going to instead use the limit comparison test. So we're going to use the limit comparison test. We're going to let a sub n be the series we are given, and then b sub n is going to be the comparing series. So we need to calculate the limit as n approaches infinity of a sub n divided by b sub n. So this would be the limit as n approaches infinity of the square root of n plus 1 over n squared plus 1. And instead of dividing by the fraction b sub n, I'm going to instead multiply by its reciprocal. So a very common technique. I'm not going to divide by b sub n. I'm going to multiply by its reciprocal. And now to make this limit as easy as possible for us to evaluate, we're going to group together the similar terms. So we have a square root of n plus 1 divided by a square root of n, and then we have an n squared over n squared plus 1. And to evaluate this limit, we're going to go ahead and break it up into two parts. We can think of the limit of the first times the limit of the second. And furthermore, we can even with that first put the limit inside the square root. So the square root of the limit as n goes to infinity of n plus 1 over n multiplied by the limit as n goes to infinity of n squared over n squared plus 1. And now we really have everything we need. For the first limit, it's degree 1 over degree 1. They both have leading coefficient 1. So that limit has value 1. For the second limit, degree 2 over degree 2, they both have leading coefficient 1. So the value of the limit is 1. When we are using the limit comparison test, what we need to be true about this limit is its value to be between 0 and infinity, which 1 certainly is. So since the sum from n equals 1 to infinity of our comparison series converges, and the reason it converges is it's a p-series with p equals 3 halves, which is bigger than 1, it follows that the series we are interested in, the sum from n equals 1 to infinity, square root n plus 1 over the quantity n squared plus 1, converges by the limit comparison test. So a bit going on with this example, but note kind of that generic or general intuition that we have. We want to apply the comparison test, comparing to kind of the biggest parts of the top and the bottom. There's no obvious comparison in terms of an inequality, which leads us to think about using the limit comparison test instead. So let's consider the given series. Looking at the form, we see both powers and factorials. And whenever we have both powers and factorials present, the observation is to maybe attempt the ratio test. So for the ratio test, we should indicate, what the sequence is we are summing up. A sub n is 5 to the 2n, and note that you can really write this as 5 squared to the n over n factorial. So 25 to the n divided by n factorial. And for the ratio test, we need to take the limit as n approaches infinity of an plus 1 divided by a sub n. So that would be the limit as n approaches infinity. An plus 1, we take a sub n, and wherever there is an n, we replace it with an n plus 1. So 25 to the n plus 1 divided by n plus 1 factorial. And once again, instead of dividing by a sub n, we are going to multiply by its reciprocal. So n factorial divided by 25 to the n. And what we need to do is simplify algebraically so that we can evaluate this limit. So in the bottom we have 25 to the n, which cancels off the n in the top, leaving us with a single 25. And as we've seen previously, that n plus 1 factorial in the bottom can be rewritten as n plus 1 multiplied by n factorial, which leaves us with just a single n plus 1 in the bottom. The value of this limit is 0, and because 0 is less than 1, we can now conclude that the series converges by the ratio test. So the sum from n equals 1 to infinity of 5 to the 2n over n factorial converges by the ratio test.